Hey, good day. So today we are to discuss one of the miscellaneous topics for the design and analysis of flexural members. So this is the computation of the nominal shear strength of unstiffened or stiffened web members. That is the B sub n equal to 0.6 of Fy A sub W multiplied by the C sub B. So we have several conditions. So we have the first one. This is for the webs of I-shaped members when that is the H divided by T sub W. So again, if you are to recall, so from the previous discussion, H over T sub W is the slenderness ratio for the web. If it is less than or equal to 2.24 multiplied by the square root of E divided by Fy, we can use the value of C sub B equal to 1.0, and our factors for LRFD is 1.0, and the factor of safety for the ASD is 1.5. Okay, for the next case, for webs of all doubly symmetric shapes, singly symmetric and channel except round HSS. So we are using a reduction factor of 0.90, LRFD, factor of safety of 1.67 for the ASD. So all we have to do is compare the value of the slenderness ratio to this values for every case. So this table gives us the summary or the guidelines on how to compute for the nominal shear strength of unstiffened or stiffened webs. So let us just recall how do we compute for the slenderness ratio for the web. That is the H divided by the thickness of the web. So this is basically equal to the total depth of the beam or the section less the value of this is less twice the value of K des. To be more specific, this is K des divided by the thickness of the web. So K des, this is the design distance from the outermost face of the flange to the web toe of the fillet in the web. So this is that distance K des. Okay, so this is the K des. So we have on the top flange and on the bottom flange. So we have also this distance. Okay, so again, that is the K des. So as you can see, so we have one on the top flange, one on the bottom flange. So how do we compute? Okay, how do we compute for the value of H? Basically, that is the total depth of the section less twice the value of K des, then to be divided by the thickness of the web. Okay, so let's have an example. Okay, how do we compute for this topic, the computation of the nominal shear strength? Okay, so let's have this example. A W21 by 55 with Fy equal to 50 KSI is used for the beam and loaded as shown. So we are required to check its adequacy in shear. So we have this beam, so carrying a dead load of 29.20 kilonewtons per meter, including the beam weight, and a live load of 58.40 kilonewtons per meter. So for the properties of W21 by 55, so we list down the properties from our database. Take note that if we are dealing with a W section or a wide flange, so this section belongs to the I section. Okay, we are considering wide flanges as I section. So therefore, we need to compare the value of the slenderness ratio H over T sub W to this value, the 2.24 square root of E divided by Fy. So we have the Fy is equal to 50 KSI So we have this is Fy is equal to 50 kips per square inch. So we are to multiply this one to 6.895. Okay. To convert the value of Fy to megapascals. So we have the value of Fy is now equal to, we have 50 multiplied by 6.895 is equal to 344.75, or let's say as a whole number, let's say we are using 345 megapascals. So these are the properties of the W21 by 55. Okay, we need the value of the slenderness ratio for the web, that is the H divided by the T sub W. Again, this is equal to the total depth of the section minus twice of the K des, then divided by the thickness of the web. So we are to substitute. So we have the total depth is 528. This is 528 millimeters. Okay, minus twice of the K des is 25.9. Then to be divided by the thickness of the web, that is 9.53. And it's equal to we have 528 minus 2 times 25.9. Okay, then to be divided by 9.53. So this is equal to 49.97. So this is 49.97. So is it less than? Okay, we need to check if it is less than or equal to 2.24. This is multiplied by the square root of the modulus of elasticity divided by the value of Fy. So we have 49.97. Is it less than or equal to 2.24 of the square root of E? For steel, we have 200,000 megapascals. And the Fy, our properties of the Fy property of the steel is 345 megapascals. So we have 49.97. Is it less than or equal to? We have that as 2.24, then multiplied by the square root of 200,000, to be divided by 345. So we have that as 53.93. So this is 53.93. So therefore, we satisfied the condition that the slenderness ratio of the web is less than 2.24 of the square root of E over Fy. So therefore, we can proceed with our solution using C sub B is equal to 1.0. We have the P sub C as 1.0 and the omega sub C as 1.5. So we may proceed with our solution. Again, that is the C sub B is equal to 1.0. The P sub C is equal to 1.0. And the omega sub C is equal to 1.5. Or maybe I think since we are in shear, I think it's more proper if we are to use, this is the P sub B for shear, and the omega sub B. So again, this is for shear. So we can now compute for the nominal strength, that is the B sub N. So how do you compute for the B sub N? So B sub N is equal to 0.6 of Fy multiplied by the area of the web, A sub W, then multiplied by the C sub B. Again, how do we compute for the area of the web? The area of the web is basically equal to the total depth of the section multiplied by the thickness of the web. Okay. So if you are to go back in our figure, the A sub W is basically this section. Okay, so this is the thickness of the web. So I hope you can see this red the red ink. I'll be using blue ink maybe. Okay, so this is our area of the web. So the total depth, and then to be multiplied by the thickness of the web. So that's our A sub W. Okay, so we are now to compute for the equivalent of the nominal shear strength. We have the B sub n is equal to 0.6. Our Fy is 345 megapascals or newtons per square millimeters. Okay, then to be multiplied by our A sub W, again from the properties of the W21 by 55, the total depth is equal to 528 millimeters and thickness of the web is 9.53. So to be multiplied by 528 mm, then multiplied by 9.53 millimeters. Then, okay, we are to use C sub B as simply equal to 1.0. Okay, so let us compute for, but before that, if we are to do unit analysis, so cancelling newtons, cancelling mm squared or square millimeters, mm, basically this is in newtons. So we are to multiply 1 kilonewton is to 1,000 newtons. So we have the nominal shear strength in kilonewtons. So we have that as 0.6 of 345 multiplied by 528 by 9.53. So to be divided by 1,000, so we can have it as 1,041.59. So this is 1,041.59 kilo newtons. So if you are to check its nominal capacity or the ultimate capacity, the B sub U, so we are using, we are to use the reduction factor or the factor, the P sub B multiplied by the B sub N. But for this case, again, for an I shape, the value of the P sub B is only equal to 1. So we are just multiplying 1. So 1.0, then multiplied by 1041.59 is simply the same value, 1041.59 kilo newtons. So we are to compare this value to the ultimate shear in our beam. So we are to compute for that value. Let us first compute for the ultimate uniform load. So for our load combination, the W sub U or omega sub U is equal to 1.2 of the uniform dead load plus the 1.6 of the uniform live load. So we're having the value of the W sub U or omega sub U is equal to 1.2 of 29.2 kilonewtons per meter, plus the 1.6 of 58. This is 58.4 kilonewtons. So we have the W sub U is equal to this is 1.2 of 29.2 plus the 1.6 of 58.4. So we have it as we can have it as 128.48 kilonewtons per meter. So 128.48 kilonewtons per meter. So how do we compute for the B sub U? So basically, the B sub U will be at the support. Since this is a symmetrical loading, uniformly distributed, then the beam is simply supported. Okay, what is the equivalent of our ultimate shear? That is the B sub U. So basically we have a B sub U is the uniform load, ultimate uniform load times the length, then divided by 2. And the same with the other side. So the B sub U is equal to the uniform load times the length divided by 2. Basically that is equal to the support reaction. So for the support reaction, that is our R, or simply our ultimate shear, the B sub U, is equal to the uniform load, ultimate uniform load times the length of the beam divided by 2. This is equal to 128.48. Then the length of the beam is 6 meters, then to be divided by 2. So what is the value of our ultimate shear? So this is equal to 128.48 times 6, then to be divided by 2 is equal to 385.44. So this is 385.44 kilonewtons. So if you are to compare this one to our capacity, that is 1,000. So again, we have the B sub U is less than the value of the P sub B of the B sub N, which is equal to 1,041.59 kilonewtons. So we can now conclude for the LRFD. So for the LRFD, W 21 by 55 is adequate. Okay, so based on our computation, so the ultimate shear is equal to 385.44 kilonewtons. It is less than the capacity of our section, the W21 by 55, which is equal to 1,041.59. So W21 by 55 is adequate under LRFD method. So let us check if it is also adequate under ASD. So for the ASD, I'll be needing the value of the allowable shear, that is the nominal shear strength divided by the factor of safety for shear. So we have that as 1,041.59 kilonewtons. This is to be divided by the factor of safety. The omega sub B is equal to 1.5. So to be divided by 1.5, and this is equal to we have 1,041.59 kilonewtons to be divided by the factor of safety, that is 1.5. So we can have it as 694.39. So let's say this is 694.39 kilonewtons. Okay. So let's have the allowable shear from our loads. That is from the allowable uniform load, we have the dead load plus the uniform live load. So we have the allowable uniform load is equal to, we have 29.2 plus the 58.4 kilonewtons per meter. So we have omega sub A is equal to, or W sub A, 29.2 kilonewtons per meter plus 58.4. So we can have it as 87. So this is 87.6 kilonewtons per meter. So how do you compute for the allowable shear? So B sub A, so this is basically the same as the support reaction. So our B sub A is simply equal to the uniform load times the length of the beam divided by 2. So equal on both sides. So we have the B sub A is equal to a uniform load, allowable uniform load times the length of the beam to be divided by 2. So this is 87.6 kilonewtons per meter multiplied by 6 meters to be divided by 2. So it's the value of our B sub A is equal to 87.6 times 6, then divided by 2. So we can have it as 262.8 kilonewtons. So the value of B sub A is 262.8 kilonewtons. So this value is way less than, it is less than 600, or it is less than the B sub n divided by the factor of safety, which is equal to 694.39. So 694.39 kilonewtons. So if we are now to conclude using ASD method, so for the ASD, we can conclude that the W21 by 55 is adequate. Okay, so since the allowable shear is 262.8, the actual allowable shear is less than the allowable capacity of the section, 694.39 kilonewtons. So under ASD method, W21 by 55 is adequate. So this will be our solution for this example.